talking about one-digit multiplication and what sort of problems we can find with that through different forms of modelling.
Thank you for the introduction. So let's start the presentation here. Works. Okay. So I'm very happy to be here. I'm going to introduce you the work that I've done with my colleagues, supervised by Professor Legenstein from Institute of Theoretical Computer Science and Dr. Ebner from Department of Educational Technology at Graz University of Technology. And what I want to just introduce you to here at first, I want just to tell you the main idea of this work we had, just without going into detail, just the idea what we had at the beginning. And then before I go into details, I want to introduce you the previous work we have done, which is actually a pure statistical analysis, has nothing to do or less to do with real learning analytics. And then I introduce to you the structure of our model of misconceptions and how we train the model and learn the parameters. And then I go into future work and tell you what we can do maybe in future. So what is the main idea behind this work? We wanted to just model the misconceptions of users in one-digit multiplication problems. This is the research work of my PhD. I focus on basic mathematical operations in primary school. And in this example, it's about one-digit multiplication questions because it's a basis in skills. And if the children has learned that very well, they have less problems in multi-digit multiplications and division and so on and so forth. There are lots of research work and discussions in the area of psychology which talk about the cognitive misconceptions in brains of children and what sort of stereotypes they cause in the praxis while they try to solve these problems. And this was our first attempt to somehow model these misconceptions. We are also very new in this field of machine learning statistics, and we had to learn all these concepts, so we are really new to this topic, and this was our first attempt to do something in this direction. And I'm very happy to be here because maybe you can give us some, or give me some comments, what we could do wrong, what we can do better, and so on and so forth. And we used probabilistic graphical models based on Bayesian networks to infer those misconceptions that are hidden, that are not visible to us from the visible data that we have, and that is actually the answers of the students to the questions that we can observe. And after we have that model and trained the model, we would like to be able to predict the future students' answering behavior. So how do they answer to the posed questions? And we want to see how this can influence the learning decision process within learning application. So a short history to our previous work. We have derived most prevalent stereotypes that are detected or defined by the psychologists in the last decades. There are lots of investigations since 1950, 1960 in this area, and they claim that these stereotypes that they have defined that I'm going to introduce you later, they are caused by some cognitive misconceptions. And we explored those misconceptions in our data set that we had and tried to find some correlations, specifically between those stereotypes and the phenomena of problem size effects that is very well known in one-digit multiplication problems, which I'm not going through in this presentation. And we explored also the most difficult and easy problems, set of problems in this area, which is pure statistical analysis. And then we tried to cluster those problems to three distinguished different groups, difficult, intermediate, and easy questions. This is what we want to have at the end. And the problem with all this statistical analysis is that there's no model behind that. It's static. It's a snapshot of the current status that we can read out of our data set. So if you want to have a data-driven learning application, which bases on these misconceptions, we cannot go further with that. We need to go a step into learning analytics and have a kind of adaptability in our system. Therefore, we came to the idea of probabilistic graphical models. The question is if it's exactly the appropriate approach. Graphical models is questionable. We can discuss on it. I would appreciate if you give me some comments and ideas if we can have some other approaches for this goal. But this is what I'm going to introduce to you today. We have the data set that we have is from a learning application. 1x1 application is called Trainer, that we have developed in our own university. It's about, I think, 4 years ago. It has been applied in different schools in Austria, Switzerland, and Germany. So it's also in the language of application in German, so in German-speaking countries. And we don't have any demographic information about the users, about the age or gender, whatever. We have the only thing that we have from this application is the answers of the students to pose questions. So we have a limited information. And we trained a model based on the data set from this application. This is a view of the statistic view for teachers when they work with the application. We have anonymized the page, so we have removed all the names of the students here. And this shows you have here 90 columns. Each represents one question that the user has answered to. And dark green means the user has mastered the question, knows that very well, no any training needed. Light green means, okay, it's satisfying, but still training is needed. And red means it's a disaster. Okay, he has not learned that specific question at all. And gray means, well, we can make no statements. We have not covered that question yet. And in the background, a kind of competence measure is calculated there, which is visualized by colors. And the teachers can directly see which student has problems in which area, and they can intervene if required. This is the status of the actual status of the application, actually. I just talked about also the easy and difficult questions. This is a heat map that shows exactly the difficult questions that have been identified. This is the first operand, and this is the second operand. And we had about 790,000 records in our data set. So you can see that the operands, the questions containing operand 8 and operand 7, they turn out to be the most difficult questions, the most unknown questions to the users. We looked also into the set of already known questions to users. So these are the questions that didn't need to be trained by the users. They were already known to the users. And interestingly, this is the average time consumption in this set. And interestingly, if you just compare here in the presentation, compare the two heat maps, you see that there's a strong correlation. This is what we could find out. For those questions that are identified as difficult, the students have needed more time to solve those. Although they have solved correctly, they have known that, but they have needed more time to solve those questions in comparison to the easy questions. And the last step, we were interested to find out 3 different different clusters of questions according to the difficulty. We just used K-means algorithm at that time, and we found a very a little group of very difficult questions containing 6 questions, as you can see here. And you can see again the operand 8 and 7 here. And then the second big group was the intermediate group, consisted of 20 questions, and the rest of 60 questions were actually clustered as easy questions. Okay, and this is about the error types I talked about that comes actually from the field of psychology in area of 1-digit multiplication problems. And this is sorted, according to the frequency that they happen by children. The first one is the operand errors. That happens when the child just make a mistake and just takes a neighboring operand to calculate the question. Operand intrusion happens when a digit actually intrudes into the result, into the answer that's been submitted by the user, a digit of the correct answer, as you can see in this example. And we have consistency errors, which also happen very often. The terminology comes from language learning, and there are two words that have similar pronunciation or said to be consistent. And here we have also unit consistency and decade consistency, as you can see. And then off-by errors, where the answer of the student is very close to the correct answer, but we have a distance of 1 or 2. And pattern errors and confusion errors happen rarely, actually, but we can also observe in our data set, as you can see. Okay, and these error types, these categories actually are effect of some cognitive misconceptions in mind, okay? And we have taken these error types as indicators of those misconceptions. And again, it's questionable if you talk about neuroscience and cognitive science, where we are not expert at all, if it's the correct way to do that or not. But we have taken these error types as misconceptions, or maybe it's not the correct terminology. I should say malknowledge probably is a better terminology for that. And our model belongs to the set of perturbation model, with a set of malknowledge elements, and the taxonomy of misconceptions contain these 6 error types. We have added additionally the category of unclassified errors, because in every data set you can find some errors that you cannot assign to any predefined categories. This happens also in our data set. Although we have cleaned up the data set and removed all answers which doesn't make sense, or the users which have played around with the application and not really severely tried to learn through the application. Although we have these unclassified errors. And then we also added this set of correct answers, because it doesn't fit actually in perturbation model, but we want to model the overall behavior, answering behavior of the student, and correct answer belongs to answers. We consider that as absence of misconception or absence of error. Okay, the first step was to create the model, create a probabilistic student model, and to create that we need to make some assumptions. The first assumption is that these errors do not depend on each other. There is no dependencies on those errors, okay? We could find in the literature of psychology no evidence that shows there is actually a dependency between those error types, but also we could not find any evidence that shows there is no dependency, so we cannot know that actually really. We assume that there's no dependency, but what we know is that the answers to the questions actually depend on at least one of those misconceptions, okay, one of those error types. It can depend also on many of those error types, multiple error types. As an example, if a child answers 41 to the question 8 times 5, okay, per definition of error types, it could be a consistency error or an off by 1 error, okay? But for a specific student that answers 41, the question is which one is the reason of this incorrect answer, and if both somehow are the reasons, which one is the more dominant, okay? And this is something that we have to learn while we train our model. This is actually the structure of model. At the top we have the learning state, which is a random variable, a multivariate random variable. The outcome of this variable is our 8 defined misconceptions or error types. And the children of this variable are 90 distinguished random variables, each showing the possible answers to a specific question, because in 1-digit multiplication questions we have 90 problems. So we have this actually causal relationship, right? So the answers that is given by the user depends strongly on its learning state and this distribution that you have here, okay? And this distribution, these probability values, they're estimates, okay? They've been learned by the model. They're not exact measures of the actual learning state of the user. They're only estimates. This is what we have to say. It's not static. It changes, right? So after every step, when the student answers a new question, this is going to be then adopted. It changes continuously. Yeah, so the learning state of knowledge changes over time, so what I mentioned, and the model represents our estimates. Okay, yes, and the more data we have, the more certain we will be which error type is more dominant and how much this dominance is, okay, with all estimates. So we can come up with a statement, for instance, an example that a particular person when dealing with one-digit multiplication problems makes, for instance, 20% open errors, 10% consistent errors, and so on and so forth. This would be a learning state of that particular student. And after we have that, we can then uncover the similarities and differences between the students. Okay, we say we can find out similar students who have somehow a similar distribution in learning state. So. And the elements of our model and the dependencies show us the overall structure of the model. And now the question is, we would like to actually quantify these error types. Okay, we are interested in to know. To what extent, to which error type these answers of the user are dependent, and to what extent, okay, which means, for instance, which answers are caused by a specific error type and how is the probability of that. And we can reach this goal by learning training the model and learning the model's parameters. In this case, because we have multivariate random variables, we have used the layer-Harper parameters for learning state and for each child node of learning state. We have used uniform priors in this case because we have no prior information about the students, how they perform while solving the problems. And so we've used non-informative uniform priors for that, which means that actually here we have all, in the prior case, we have all equal probabilities at the beginning and first step. Not only here, but also here, we have actually equal probabilities for the error types and also for the correct answer. And we try then to infer, when the user answers a question, we try to infer the correct distribution that causes that specific answer. Okay. So given a specific type, the question is to find out the tendency towards a particular answer, and this is done by expectation of the EM algorithm that we've used, applied here, because the learning state that we have at the top is hidden, and we want to infer that hidden status from the observable status is the learning state. We have used, that is the answering behavior of the users. We have used the probabilistic programming library Figaro for Scala programming languages to solve that problem. And actually that's it. That is the status of the work we have already done. What we can do for future work, we can probably find more error types. It depends on the dominance of the category unclassified error. It is high, then we have to go into that category and see if we can just find more error types. We can identify stereotypes with mixture of the Dirichlet distributions. Could be also in other future work. We can predict the answer, okay, that the user would give to a posed question. and according to this prediction, we can decide probably what the next learning question could be, okay? And the main topic would be, a very interesting topic would be in the future is to maybe rearrange the question sequence in the application. And the question is how we can do that. So it's a big question mark for us. Okay, I'm actually finished, exactly on time, I think. And thanks for your attention. And I appreciate really if you just can comment on our work and just give more ideas what we can do better or which part is not really appropriate for these goals. Thank you.
Okay, thank you. So again, time for a couple of questions.
Or comments.
Or comments.
You mentioned the question sequence. So now the questions are asked in a fixed sequence or randomized order?
Well, it is not exactly randomized. There is a very, very primitive algorithm behind that, which has been developed 4 years ago, but it has actually nothing to do with Bayesian networks. It's a very primitive algorithm. I have not in mind how it works, but it's actually very primitive.
Yeah, but can it have impact on the data that you collect? For example, the errors can be caused by the ordering.
Pardon?
Doesn't the ordering of items have an impact on the mistakes, for example?
Could be, yeah. I cannot deny that. The point is, if in the future work we can define this kind of rearrangement of sequence of the questions, okay, and compare it with the actual current status, if we can observe any kind of improvements. Actually, I expected to hear lots of comments about my work, because maybe the reason is it's the last day and many participants have traveled back. It's a bad luck, but...
Okay,
So, okay.
thank you again.
Thank you very much.